Hello, everyone, and welcome to our webinar on contact tracing and reopening businesses with SafePaths. And today I'm going to talk about two key ideas. One is about using machine learning in a privacy-preserving way and also using Wi-Fi. As we have discussed in the previous webinars, the SafePaths platform has a citizen-facing SafePaths app as well as the dashboard for public health and for businesses. And in terms of the proximity technologies and APIs, our goal is to support privacy-preserving solutions for GPS, Bluetooth, Wi-Fi, and others. And our partner PathCheck Foundation supports these apps. We already have apps that are being built for public health and new start solutions for countries and states and employers that are open source, privacy first, and interoperable. The V1 was about GPS. The V2 uses Apple and Google Bluetooth APIs, and V3 will be larger set of solutions for public health. And the PathCheck Foundation is launching a project Aurora that's based on Google Apple exposure notification with risk calculator, symptom check, public health information. However, this does not have the GPS location. So SafePaths in general is providing a plethora of tools. Our goal is not to promote a single app, but to help everybody else launch their own apps and servers and dashboards. And so at MIT, we continue to focus on the algorithms and think tank behind it, but the foundation is also working very closely with government, public health, and employers to provide corresponding solution, including creating support solutions for manual contact tracing. And so the COVID SafePaths Alliance has, of course, MIT faculty and MIT scientists, but also works with a wide range of partners in conversations with WHO and HHS and Mayo Clinic and so on, of course, with the PathCheck Foundation. But if you really want to solve COVID-19 related issues with privacy-preserving software, the individual's workflow is not just about the exposure notification or contact tracing, but it's also about symptom checking, triage, telehealth, figuring out whether you need to be quarantined, verifying that quarantine, and again, bringing this individual safely back to their work or school environment and closing the loop with public health. And the magic is, how do we achieve all of this in a privacy-preserving way, which is that without the name or any personally identifiable information about this individual, how do we provide this experience so that especially those who are distrustful of government-mandated programs or people who are often discriminated against would feel very safe in participating in this ecosystem. And for that, we have to make sure that we preserve privacy but also many other things. It's about consent, it's about regulation, it's about trade secrets, and it's also about the incentives. And same is true for businesses as well as they think about the experience flow for their workers and employees. So SafePaths is really working with a range of stakeholders, whether schools, workplaces, labs, healthcare, insurance, and providers, to see how we can create solutions that are privacy preserving as well as interoperable. And at MIT, we are very focused on a series of research efforts and standardization efforts that use these proximity APIs and still preserve privacy and interoperability. So some of the work you will see on our website, we are putting out our drafts as we go, is how can we add a location context in an encrypted manner to the Google Apple Bluetooth API? Or how can we use Wi-Fi for co-location while maintaining privacy? Or how do we use GPS to GPS intersection between two smartphones using a secure multi-party computation? Or how can you update the symptom checker maps using differential privacy? Or how can you use techniques like split learning so that we can do distributed machine learning on smartphone devices without looking at raw data? and so on. So if you are a researcher, you're a scientist, or you want to contribute, please join our GitHub in this very open source manner. We are writing these papers. We have weekly meetings that you can participate in these conversations if you would like to work on any one of these research or algorithmic problems and contribute to open source at MIT. So I'll give you an example of 3 projects. One about Bluetooth plus GPS, second about Wi-Fi, and third about machine learning in the context of COVID-19 in a privacy-preserving way. So one modification to existing Google Apple exposure notification API is to add GPS information in an encrypted way to the Bluetooth broadcast. In this sense, GPS is not being used for looking at intersection of the encounters, and there's no GPS logging in that sense, but the GPS location is revealed only when there's an exposure, only when there's an encounter that's revealed to otherwise healthy person. The other interesting opportunity is, can we use Wi-Fi for co-location? And there are 2 ways to think about it. The most common way to think about this is every Wi-Fi access point can keep track of the MAC addresses of the smartphones to which they're connected. And in that sense, those access points create a proximity group. And then if one of the smartphone belongs to a person who's infected, then everybody else in that proximity group can also be informed. And this will be a top-down system that won't even require anybody to download an app. But it has certain issues of privacy and being able to alert people in a short amount of time. The second solution is based on smartphone, where instead of outside looking in, the smartphones are looking out. They're looking at all the access points that they would see and keep a list of those list of access point MAC addresses on the smartphone. And if one of the phone is infected, they can upload their MAC addresses of APs that they have seen, and all the healthy people can download. This unfortunately doesn't really scale because it has serious privacy issues, and also the amount of data you would have to download would be unmanageable. So we have a series of papers coming up, some of them already on our GitHub website, that talk about how can we do Wi-Fi co-location in a privacy-preserving way. So we would love to work with you and implement some of these solutions. And some of the early prototypes are already being built. Let's come to machine learning, right? How can we train machine learning models without exchanging raw data on phones through questionnaires or some of the sensors on the smartphone? So symptom checker, self-assessment, quarantine, all these are actually gathering a lot of information on the smartphone. But because of privacy, we cannot just suck up that data from the individual smartphone and create a global AI. At the same time, there are other solutions. You can cuff into a phone, and based on the sound, there are techniques that could detect what kind of pneumonia you have. And these algorithms are out there, but they're not improving dramatically because millions of people are not able to use these apps. Millions of people are not able to use these apps because of, again, privacy issues. So how can we solve this problem? The simplest way to do this would be to anonymize the data, but that's not much of a privacy. The next would be to obfuscate, which is add some noise to personally identifiable data, but that would challenge machine learning systems. The performance will degrade. Probably the best solution is to do a homomorphic encryption, but that would again interfere with ability to create a global machine learning model. So 2 solutions have emerged over the last few years. The next question for us is, how do we use machine learning for COVID-19? And how can we train deep neural networks without exchanging raw data on the phones? Because these phones are accumulating a lot of information from questionnaires, from quarantines, and so on. And also you can imagine a lot of the sensors are being used for diagnostics. The one way to do that would be to anonymize, but that's not privacy at all. The next would be to add some obfuscation by adding noise and techniques such as differential privacy, but that interferes with machine learning as well. Probably the best solution is to use encryption, especially homomorphic encryption, but that doesn't allow us to create full-fledged machine learning models. So 2 techniques have emerged. One is called federated learning, which is being promoted by Google, and another technique called split learning, that's from our group at MIT. And SafePaths AI would allow us to train these machine learning models while maintaining privacy for individual. and we call it smashing of the data. Let's say you want to create an algorithm to detect pneumonia in chest x-rays from COVID-19 patients. It would be nice if all the hospitals would simply upload all the chest x-rays that they're encountering. But that would be difficult to do because of HIPAA regulations and trade secrets as well. So instead of the centralized algorithm, we could do collective intelligence, where I could take 100 interns and send each of them to one hospital, and they can learn from the local population about how to detect a pneumonia from a chest x-ray. Maybe the first hospital has more diabetics, the second hospital has more smokers, the third hospital has particular ethnic group, and so on. And these interns can come back and we can have a collective intelligence. And the beauty is that the interns won't bring back the raw images or information about the patients, but they'll be able to collectively take any new x-ray and detect if it has a pneumonia that's consistent with COVID-19 diagnosis. And this collective intelligence is an idea behind federated learning, where machine learning models at each of the hospitals would partially train on whatever x-ray images they have and create those models, and only send the models but not the raw data to a central authority that would, in simple words, average all those models and create a better AI. The other method called split learning is from our group here at MIT, and it's more like the elephant and the wise man, the blind man. So each of them cannot look at the elephant, but they can provide a description of each of the features they're seeing. You know, the person who's looking at the trunk might say, hey, this looks like a snake that's this long. And the woman that's looking at the body of the elephant might say, hey, there's a wall with this type of a texture. So without revealing what the elephant is, each of them can convert this phenomena into a set of feature vectors. And this idea is the basis of split learning, where instead of sending the raw x-rays, you can actually reduce the x-ray into a few bytes of information about the description, the features of this x-ray. And that smashed wisdom is what's sent to the server, and the server can train and infer from this smashed wisdom as well. And to be precise, we take a deep neural network and we split it, and early layers execute at the client and the later layers execute at the server. And these early layers can convert the raw x-ray into a smashed wisdom. You know, a 10 megapixel x-ray, we can possibly reduce it down to just a few kilobytes as well. So to conclude, to overcome COVID-19, we need a range of solutions. New types of proximity APIs that are based on Bluetooth or GPS or Wi-Fi, as I described, as well as new machine learning and AI tools that can create a global AI from localized information on each of the smartphones. So what we're really trying to do is create a bird's eye view into everything that's going on. But a bird's eye view in a digital system can easily lead to a surveillance state. And so without creating a big brother, how can citizens and communities coordinate with each other is the real problem. And at SafePaths, we are providing that with three key ideas. One is privacy preserving, second is interoperable, and third is that it's open source. So in the short run, we hope to overcome the challenges for public health. In the medium term, it's about restarting the economy, and over the long term, it's about building resilient societies. So please join our GitHub page, which is at safepaths.mit.edu. And please join us if you're interested in working on many of these research topics, contribute to algorithms, or participate in the open source code. Thank you.